In this video, we will be talking about another lesson that's part of general mathematics. This is all about domain and range. I can see that I've already made a couple of videos a few months back about domain and range, but right now, this is senior high school. Um, the concepts here are a lot more expounded on. Uh, the videos that I've made in the past months relevant to this lesson are based on the difficulty of the last year of junior high school, which is grade 10. Um, to anyone who is wondering what curriculum I'm speaking about, um, it's all in the Philippine curriculum, K to 12. So yeah, let's start. For domain and range, uh, let's see. Um, all the possible x values of a function. What refers to this statement? Uh, all x values. So in a table, we have x, y. So this is what we refer to. The x values are written here. And other x values could be written as, say this is set A, and this is set B. So yeah, and we have elements here that correspond to their that fall to their corresponding sets, and they usually match. So those are two particular applications or where we could see x values. So obviously, based on the previous video that I've made, um, domain refers to all the x values of a function, while range refers to the y values, obviously. So now that we know that domain refers to the x values, range would altogether refer to the y values. And so yeah, we have a few examples to cover. So let's start with this one. Input and output, assuming that input refers to x and output refers to y. So for domain, these are the x values. So the domain, we have -1, 0, +1, +2. For range, we have -3, 0, +2. So these are everything for the domain, and these are everything for the range. There you go. Next question. So there isn't any specific label on the given two sets, but yeah, obviously this is going to be set A. Anything that's at the left would be set A, and at the right would usually be set B. So set A refers to the domain, set B refers to the range. So let's enlist all the elements that fall under domain, aka set A. -1, 0, 1, 2, and 3. For range, we have 3, 5, 11, and 21. Those are the final answers. Okay, let's move on. So here, domain and range. So this is quite different. The way we extract the elements of domain and range in this particular problem is quite different in comparison to how we find those elements in these types of examples. So it might be confusing at first, but you'll realize later on that it's pretty easy. So in a Cartesian plane, just know the coordinates. So this one is 1, +1, comma 5, which is just 1, comma 5. So we know that the x values are here and the y values are at the right side. So in that sense, we could say that domain is 1 and range is 5. So let's enlist more. Next period, we have, I I am quite feverish right now, so yeah. Pardon me. I beg your pardon in advance. Number three, that's our domain, and for our range, it refers to 5. Still 5, we don't have to write it 2 times. If we have the same integer already written, we don't have to write the same integer again. So the third coordinate, it's 4 and 2. For the last coordinate, we have 6 and -2. So these are the final answers. Alright, let's move on. Oh, let's just consider this as a bonus. I'm supposed to remove the final answers, but yeah. Let me explain why the domain and range are both R. R, in other words, there's another way to write this final answer. It's basically -infinity, positive infinity. When we want to look the domain in the Cartesian plane, you have to look from left to right. You start from here all the way there. And if we want to look for the range, we start from the bottom all the way to the top. So that's that's a basic law that we're supposed to know whenever we want to find the dominant range of whenever we want to find the elements of dominant range in a Cartesian plane based on a specific graph. Usually they're functions. They're written as functions, not graphs, but yeah. Anyways, for this particular graph, this is usually x raised to 2. So let's say f of x is equal to x raised to 2, positive x raised to 2. This is a quadratic function, and this is basically what you usually see in quadratic functions. But for x raised to 2, realistically, it's located here. The line is located exactly here. But yeah, that's not our focus right now. But I think we do get the point. We don't have to exactly master specific details about the line's location in the Cartesian plane, but we could already know that since the function is quadratic, there's a good chance that the dominant range are both set of real numbers, not aka -infinity, positive infinity. So coming from the left, you know that this line will never end since it's an arrowhead on both sides. So -infinity, positive infinity. When it comes to range from going down from bottom to top, we know that it's also unending, -infinity all the way to positive infinity. So yeah, you might want to take note of quadratic equations usually being always like this in terms of domain and range. They're all set of real numbers, but of course there are possible exemptions. It's up to you if you want to venture out to see all the possibilities of the dominant ranges of quadratic functions. So yeah, this time, hang on, I think, wait, I think I've made a mistake. I'm really sorry. This is x raised to 1. This is a linear function, not quadratic. This is linear, while quadratic is usually like this, like this, like this, or like this in the Cartesian plane. So yeah, apologize for that mistake. I suppose this is the quadratic. All right. So for the domain, we know that these two arrowheads will never end in terms of distance. But then for domain, from very left to very right, we know that it's negative infinity all the way to positive infinity. Or in other words, the domain is the set of all real numbers. As for the range, it's from 2, positive 2, all the way to positive infinity. Why? Well, as you can see here, initially, generally we know that range, if you want to measure the range, we start from the way bottom all the way to the top. And right now, this is the very bottom of the line. So in every constant, we encase it with a bracket, not a parenthesis. A parenthesis is only exclusive to infinity values or in certain exceptions. One instance, whenever the point is a hollow point. I know there are other exceptions that excuse an integer from being encased with a bracket and instead being encased with a parenthesis, but that's another day's topic. So for range, this could already be a decent answer, but there is another way to write this one, which is this. So y, this is actually set builder notation. Writing answers in set builder notation, I think, would become in handy, especially if you're trying to answer finding the dominant range of root and rational functions, as it's really difficult to graph those two types of functions. So y is greater than or equal to positive 2. So the range will always be equal to or greater than positive 2. I think that's self-explanatory. Just takes a few minutes to understand, and yeah, we'll be able to appreciate the beauty of this kind of mathematics. So next problem. So the domain, as you can see here, the arrowhead goes all the way to the left and another arrowhead goes all the way to the right. So obviously the domain is the set of real numbers, or negative infinity all the way to positive infinity. Right. For the range, it's quite limited actually. So starting from here all the way here, it's just 1, 5. That's the range. Right. Next graph. So this time, domain and range, they're both limited. So this is the very left and this is the very right. The very east and west and east of the Cartesian plane. So this is 1 and 5. For the range, this is also the very bottom, the very south of the Cartesian plane, and this is the very north, which is 4. So these are the answers. These are the domain and range. Two more examples. Right, for the domain, there are no arrowheads, so the quantities are limited. Obviously, we'll be using brackets to encase these constants or integers. So here at the very east, I mean west, it's positive 1. At the very east, it's positive 5. For the range, we start, the very south is positive 1. The very north is positive 5. So I don't think it's a coincidence that the domain and range had the same values. I don't know. Next, this time we have arrowheads. So in this particular sense, whenever a parabola is written like this, obviously the domain is already the set of all real numbers, or aka negative infinity, positive infinity. Right, for finding the range, so this is the very south, which is basically positive 2, uh, but then it extends all the way to the top, so there is no point of limit, so this is positive infinity. Of course, encase it with the parenthesis, encase constants with bracket under normal circumstances. Right, next, so this time we have a hollow point. Usually our coordinates are symbolized as this one. Hollow points, on the contrary, are written like this. I hope you can see the difference. So for the domain, so this is the very left, so it's negative 2, and the very right is positive 4. So because it's a hollow point, negative 2 is situated as a hollow point, we put parentheses. That's an excuse for integers. Integers are allowed to be encased with the parentheses in the event that they are labeled as part of a hollow point. Right, so positive 4, still a bracket, since it's not a hollow point. For the range, all the way to the bottom, this is, I suppose, negative 5. And the very top, the very north, is positive 3. So I suppose that does the job. These are the final answers. So let's read on these on this particular detail. Sorry. Hollow points make the integer get encased by parentheses, not the usual bracket. So that's basically what I said earlier. Alright, we're given this particular example. Alright, for the domain, they're all limited. Obviously, there's no infinity here. And so we'll be using the symbol union or U. This is usually a symbol that you could that you learn in the concept of sets. It's usually introduced during the first quarter of your first year in high school, in grade 7, here in the Philippines. But then yeah, a lot of schools have different curriculums. You could learn this anytime, at any year in high school. But the important thing is, right now in senior high school, you should have already know this. So for the union, let's say, let's find the domain of this particular line. So it's negative 4, negative 2. So union. Then let's move on to the next line, which is negative 2, positive 4. Oops, sorry, this is 0. And we also place another union, and we enlist the domain of the last line, which is positive 6, positive 8, then bracket. As you can see, these are the hollow points, 2 and positive 6. So I'm sorry, 0 and positive 6. So they're the only ones written or encased in a parenthesis. The rest of the constants are encased in brackets. We connect these the domains of these lines through the symbol union. Right, for the range, first line, this is negative 2, and at the very north it's positive 2. Union, so here this is the very bottom, so negative 2, and the very top is positive sorry, it's 0, I suppose. Yeah, it's 0. Union again, that looks more like a V. Let's fix that. For 6 we have this. So sorry, this is quite messed up. So right now we both have a normal coordinate and a hollow point, but that doesn't matter anymore since they're both in the same line. This is still 2, so we just put um, something like this, curly braces. So yeah, it's everything that we have to place here. Alright, let's move on here. So we're given half a circle. So obviously this is a function. If you put a vertical line test, you can see that there's only one intersection, therefore it's a function. For the domain, so as you can see, their very ends are hollow points, are labeled with hollow points. So for the domain, it's -4, +4. The constants are encased in parentheses since both sides are hollow points. And for the range, all the way here, 0, it's basically 0, then +4. Of course, even though you don't really see that 0 is part of the hollow point in a sense, but then they're on the same level. So obviously this is affected. So 0 is encased, not in a bracket, but in a parenthesis. Well, obviously 4 is encased in a bracket. Right. So we're done with graphs. So we have to find the dominant range given specific functions written as equations. So given f of x is equal to -x, we have to find the domain and range. So this is a linear function. So there are many ways to find the domain and range of a linear function. One in particular is we could graph the function itself. But let me tell you this in advance. It's not all the time that graphing would be the best solution or the best way to find the domain range of a certain function, for the reason that that particular function might be too difficult, or it would require you to run a lot of coordinates in the graph, especially for those functions that have coefficients with decimals and fractions. It isn't easy. What's easier is that what's easier is this technique that I'll be showcasing to you later. So right now, let's try to solve this using graphical method. So let's say I'll give a random number for x, say positive 1, 0, -1. So given f of x becomes y, then y is -x. Y is negative, then +1. Y is -1. So this is -1. So given y is -0, so this is 0 also. So given y is -1, so that becomes positive. So we get something like this. And if we graph it, so this is 0, 0, this is positive -1, and this is +1. We graph it, you get something like this. This is one of the funnest, one of the most enjoyable functions to graph, since it's really easy. And as you can see here, it's a diagonal line, and it stretches all the way to the northwest, and the other side reaches all the way through the southeast, so of the Cartesian plane. So for the domain, let me tell you this in advance. So in a Cartesian plane, usually if this was positive x, then the graph would look like this. And so in that sense, the dominant range of these graphs, negative or positive x, they both have the same dominant range. So obviously for linear function, domain and range are both are set of all real numbers. In other words, uh, negative infinity, positive infinity. So yeah, that's already linear functions. Finding the domain range of linear functions. It's one of the easiest in this lesson, since logically speaking, domain all the way there, range, domain all the way to the left and to the right, range all the way to the bottom and to the top. Diagonal lines just assuming that the lines have arrowheads on their very edges, the domain and range will always be R. So yeah, it's everything that you have to know for linear functions. So right now, number 2, it's x cubed. This is a cubic function. This is quite different in comparison to a quadratic function and a linear function. But yeah, let's graph it. Let's say positive 1, 0, negative 1. Right, cubic function. So let's say f of x becomes y. Y is x raised to 3, such that 1 raised to 3 is still 1. 0 raised to 3 is 0. Negative 1 raised to 3 is still negative 1. Dang. Anyways, we get something like this. And if you graph it, you get something like this. It's quite awkward. I don't think it's a coincidence. Maybe it is. That f of x is equal to x raised to 1. It's the same graph, I think. Maybe, maybe not. I'm just not sure. Anyways, for this particular graph, just in case x raised to 3 is equal to fx actually has the same graph as fx is equal to x raised to 1, then the dominant range are still set of all real numbers. Right, let's move to number 3. So right now, I think, if I'm not mistaken, this is a quartic function, since the value or the variable is raised to 4 or positive 4. So let's just say, to be exact or to be safe, that this is already a polynomial function. It's a polynomial. The term polynomial is a more generalized term to functions that have exponents that are higher than 3. So we know that linear is raised to 1, quadratic is raised to 2, cubic is raised to 3, I think quartic is raised to 4, then yeah, I don't know what else. Quintic, I don't know. But yeah, my teacher used to say that polynomial is a better term. But I think that's a subjective statement. Anyways, for polynomial function, I don't think we have to graph this anymore. But it's still your decision. But for now, I'll be teaching you a different method. Polynomial function. So t raised to 4, the graph is usually like this. For t raised to 4. And for the domain, obviously it's just a set of all real numbers. And for the range, it's basically 0, positive infinity. That's for number 3. For number 4, let's say, actually, let me identify this function first. It's actually a rational function. This is one of the types of functions that I've been talking about a while ago, something that we don't have to graph anymore in order to find the domain and range of it. What we have to do instead is to, like, for rational functions specifically, if the rational function is positive, this is what it looks like. And if it's just 1 over s, or let's just say 1 over x, uh, these lines will never meet 0. That also goes if the rational function is a negative. So basically, if a rational function is negative, the graph would look like this. And these curves will always never reach 0 in the x-axis, or in this line. So yeah, but in this particular problem, this is what our graph would look like actually. And with that in mind, we could say that domain will always be uh, the set of all real numbers, since they're all the way like that. And for the range, something like this. Of course, we have to write something like this, except 0. Since this is basically saying that for both the domain and range, um, these lines will touch all possible real numbers in the Cartesian plane except 0, which lies on the y-axis. There's actually another way to write domain, possibly range as well, but let me just add this up. So from the very left side, it's negative infinity, then we end up 0, then union 0, positive infinity. But why did I add parentheses? Why did I encase the zeros with a parenthesis? I think this is another exception. Constants can be encased with parentheses for this another reason, since it's a rational function and that 0 is not part of the set of all real numbers that are said to be part of domain and range respectively. So yes. Let's move on to number 5. So this is number 5 is an absolute. So for what? Fx is equal to the absolute value of x, I think. I think that's how you read it. Basically, for this particular function, this is how it looks like in a graph. Of course, this graph is not to scale. I'm not exactly a good drawer, even in this setup. But yes, for the dominant range of the absolute value of x, it's basically r, and for the range, it's 0 to positive infinity. It's basically like this kind of graph, the one earlier. Domain, all the way to the left, all the way to the right, infinity, and for the range, it's from 0 all the way to positive infinity. Right, let's move on to number 6. So this particular function is called a root function. So this is also the other type of function that I've that I've mentioned about earlier, that we don't really have to graph them specifically anymore, since it's quite difficult. So all we have to do is to make specific assumptions. This is a technique that I mentioned about also earlier, and in a few pages you'll be seeing about it. So all right, for this particular root function, 2 minus t, this is what it looks like in a graph. something like this. Uh, since there is a 2, this is positive 2. This is where the graph begins. And so for the domain, it's negative infinity all the way to positive 2. And for the range, it's 0 starting here all the way to positive infinity. You can write the domain in another way. This is how you write it in another way. T is less than or equal to positive 2. So yes. So for the rest of the pages, I'll just be discussing them in a few words. But yes, consider this as an opportunity for you to organize yourselves. Uh, I've made I've made these pages to help organize your review on domain and range, specifically on finding them given particular functions. It's not all the time that you'll be finding domain and range based on certain graphs. So I'm letting you prepare for the worst case scenarios in tests that have these in their pointers. So observe that for linear functions, this is what they usually look like. For quadratic functions, this is what they look like. Just remember that x raised to 2, positive x raised to 2 is a happy smile, and negative x raised to 2 is a sad smile. As for these kinds of parabolas, I think that's what you call it, parabola. I'm not sure what types of functions are I'm not sure how they're written in Desmos. So yes, for x raised to 3, you get something like this. It's quite wiggly. For x raised to 4, or quartic, if I'm not mistaken, to be safe, polynomial functions, it's a lot more complicated. So it's up to you. You have to ponder the more specific differences between x raised to 2 and x raised to 4, such that they're functions. So for rational functions, you get something like this. For root functions, you get something like this. And for constant functions, this is one of the easiest. Just imagine that in the parts of speech, out of all of those parts, you've learned about article being separate from an adjective, but usually in high school, articles are considered as adjectives. So that same concept is similar to this one. Concept of constant functions. This is really easy. You just have to know that in constant functions, the lines will always be vertical. Why not horizontal? I'm sorry. The line should always be horizontal. The question is, why cannot constant functions be vertical? Well, obviously, if you put a vertical line test, then obviously it's not a function at all. So yes, vertical functions will always have horizontal lines, and given fx is equal to 1, this is 1 in the y-axis. So yes, this is drawn to scale. As for the functions presented in this video, so these are the list. This is the list. So linear function x raised to 1, constant function, there is no variable, only a constant. For quadratic function, x raised to 2, cubic function, x raised to 3, rational function, 1 over x, radical function, or I don't think it's called radical function, it's called root function, square root of x, polynomial function, x raised to 4 or above. So here are estimations. This is what you have to note. Linear function, So regardless of whether x is positive or negative, dominant range are altogether R. It's everything that you have to know for linear functions. For constant functions, uh, the range will always be which number the constant function is. So if it's fx is equal to 1, then the range is 1, obviously. If fx is equal to 45, then the range is 45. I hope you get that point. For the domain, it will always be negative infinity, positive infinity, since the line will always have arrowheads on its west and east, or its left and right. So for the quadratic function, f of x is x raised to 2. Normally, if it's just x raised to 2 as a function, the range will always start from 0 all the way to positive infinity. But if the function is negative, then it's basically the opposite. So for all the way from 0, then I'm sorry, all the way from negative infinity, then you end up to 0. For the range, nothing changes. All the way to the left, all the way to the right, all the way to the left, all the way to the right. So they're basically R. Right. For cubic function, uh, I couldn't really make definite conclusions, but then they're both a set of real numbers, given that f of x is x raised to 3, or that f of x is negative x raised to 3. As for polynomial functions, set of all real numbers, this is similar to a quadratic function. We'll just have to research for the more specific differences, since the similarities are already quite obvious. For rational function, it's quite more complicated, but if you want to know how I was able to remember how to find the dominant range of rational functions without having to graph them, this is my technique for you. So for the domain, you'll always have for rational functions in general, I suggest that you write your answers in set builder notation. Speaking of set builder notation, you will always involve the symbol not equal to. So you'll always have to associate rational functions with not equal to sign if you're going to answer the dominant range in set builder notation. So x is not equal to 0, y is not equal to 0 in a way that it's 1 over x. But of course, there will be modifications. It's your responsibility to make observations based on a variety of examples of rational functions, compare the graphs, and yeah, you'll get the hang of it one day. So yeah, let's say x plus 1 or 1 plus x, you get something like this. And for x minus 1 or negative 1 plus x, you get something like this. So I'll give a conclusion here. So if there's another number beside denominator x, which is positive, then the domain will be that same number, but it's negative. And for the range, it's still 0. That also goes for this. If the number is negative, here it's negative 1, then the domain will be not equal to positive 1. Then the range will always still be not equal to 0. So the way you write it in another way, it's basically negative infinity to negative 1 union negative 1 to positive infinity. But it's I could already tell you now that it's a lot easier to write the final answer in set builder notation. So yeah, this is another thing that you have to take note of. If there is also a variable in the numerator of a rational function, the domain is equal to -1. Since this is +1, the domain will be not equal to -1. And for the range, it's +1 for some reason. But yes, that also goes if the denominator is -1, x minus 1, in other words. Right, for the root function, positive square root of x, you'll always have to associate the root function with this sign. So if the root function is positive, there's no negative sign like this one, you have to note that the domain range will always have the symbol greater than or equal to. So here it's x is greater than or equal to 0, y is greater than or equal to 0. For here, negative square root of x, the domain is, since the function is negative, the range will be less than or equal to. So the domain will still have the same usual symbol, but then the range will not. That's a specific detail that you have to take note of. So yeah, if the function is if the root function is positive, it will look like this. If it's negative, it will look the opposite. So here it's in quadrant 1, here it's in quadrant 4. It also goes for this quadrant 1, quadrant 4. Alright. Couldn't really say much about these details anymore. For the range, it's still 0. If the root function is positive, the sign is greater than or equal to. If the root function is negative overall, it's the range has the symbol in its set builder notation less than or equal to. So yeah. If the root function, if it's negative, if it's x minus 1, then your starting point is +1. Here, if it's x plus 1, then your starting point is at -1. It's also a cute little detail that you might want to take note of. And here, at this particular problem, it's 1 minus x. Yeah, I couldn't really say much about it anymore. There's also another graph here, but then it's the same domain and range with this one. Yeah, it's everything that you have to know. Let me just feel free to screenshot this part of the video, whatever helps you, but I hope you could give credit to the owner of it to avoid plagiarism. I hope this video has helped you for finding the domain and range, and might as well you may have learned about the types of functions and their likely domain and ranges in certain situations, in certain details. So yeah, that's everything for this video. Thank you for watching.